is all about something called quadratic functions. And so in 4.1, we're going to be learning about what a quadratic function is, and then a whole bunch of different keywords and terms we're going to be using throughout the unit to describe these types of functions. So throughout this unit, we're going to be looking at different types of graphs. And I'm just going to kind of look at a couple here to start. If we look at the graphs on the screen there, we've got two. It doesn't really matter what these graphs are. For now, I just want to focus on their shape. So back in grade 10, we spent a lot of time focusing on graphs that were straight lines. We called these linear functions. In pre-calc 11, we are not going to focus on linear functions so much anymore. We're going to focus on something called a quadratic function. And a quadratic function doesn't have a straight line type of a shape. It has a curved shape that looks like this. So this one is a quadratic function. So the key here today is going to be looking at different quadratic functions, checking out their shape, and then also describing them. Okay, so before we get started, or I guess to get started, we're going to graph a couple of quadratic functions on the graphs down below here. I'm going to do two by hand, and then I'm going to do two using Desmos, just to save a little bit of time. So the two I'm going to do by hand are these two here. So on this graph here, we're going to do y equals x squared. And on this graph here, we're going to do y equals negative x squared. Just to get an idea of how the shape looks, and then we're going to label some things on our graph. Okay. When you're graphing a function and you have an equation to graph it, what you want to do is create a table of values. And in our table of values, we're going to choose a bunch of x values to plug into the equation, and we're going to get y values out, and that's going to give us some coordinates that we can place on the graph. So y equals x squared. You'd like to choose both negative and positive values of x, just so you can cover the graph evenly. So I'll do these values here, just because those are the values that I see on the graph there. Okay. So when you choose an x value, what you do is you plug it into the function here. So I'm going to put the x in there, so negative 4 squared, and get 16. So this is going to be 1 point on the graph, negative 4, comma 16. We can go ahead and place that on the graph, actually, but it's way off of the screen here because my y values only go up to 10. So let's try the next one. We have negative 3 squared, which is 9. That one I can place on the graph. This point here goes on the graph like this. Graphs are a really nice way to visualize equations because they give you a nice picture. Negative 2 squared equals 4. Negative 2, 4 will go on that graph right here. And you'll see you get kind of a curved shape coming out as I do a few more points. Negative 1, 1. 0 squared is 0, so we get this point at the origin there at 0, 0. After a while, you don't have to write the points every time. You can just write what the y values are. So 1, 1. And you'll see that there's some symmetry coming out here too, because when you square negative numbers, you get the same answers as if you were to square the positive numbers. And so our graphs will have some nice symmetry to them. And then this one will, of course, be 16 again, which is off the screen. So you'll see this kind of U-shaped graph. It's not a corner at the bottom, it's a curve. Okay, so when you draw it, you try and draw a nice smooth curve there, kind of like a U shape rather than a V. And that is called a quadratic function. Sometimes also people call it a parabola, or they say the curve is parabolic. When you have negative x squared, you're going to get the same type of shape, but it's going to be upside down. Actually, I don't have enough space to graph this on here, but it'll look similar. I won't plug them all in, but it'll look like this, and your graph will be the same, but it'll be facing down like this. Okay, let me show you a few more on Desmos. I'll do the ones that they asked me to do there. So I'll do x squared plus 2x plus 1. So if you have a Desmos screen open, you just type in y equals x squared plus 2x plus 1. And you'll see it's the same parabolic shape, except it's not, so the bottom of the parabola is not at 0, 0 this time, it's been shifted over, and we'll discover like why that happens and how to see that. And then this one is negative x squared plus 2x. So you'll see this one is shifted over again, but it's also facing downward. So it turns out if the sign on the x squared term is negative, your parabola is going to be opening downwards like a sad face. And then if it's a positive in front of the x squared, it'll be opening upwards like a happy face. So I like to remember happy face means positive, sad face means downwards and negative. So if I change that to a -2, see how it starts facing downwards. So we'll discover lots of patterns like that throughout the lesson. Let's learn some keywords now that you know what the shape is. So whenever you see a quadratic function, it's going to have that type of shape, that parabolic curve shape. It's not going to be a straight line like you've seen in previous classes. So there's some more graphs there. We're going to go down to here. So again, this is called a quadratic function. A quadratic function can be written like this: y equals ax squared plus bx plus c. So you'll always see the x squared term specifically, and you may have a x term and you may have a constant term as well. And then this is called general form of the equation. We're going to see a couple different forms. And let's just read through here and highlight some of the key terms. So if you have a highlighter, you should do this as well because you need to know these words. The graph of every quadratic function curve is called a parabola. I already mentioned that. So we can say the shape is parabolic. The characteristics of parabolas are listed below. So these are some words we need to know. The bottom point on a parabolic curve is called the vertex. It could also be the top point as well. It's just either the peak or the valley of the parabola is called the vertex. Okay, so we'll be learning about ways to find where that peak is. And there's lots of different applications for why that peak can be important in word problems and things like that. So it can be a minimum point, as in this scenario here, where you're at the valley, or it can be a maximum point if you're at the peak, if your curve is facing downward. Okay. The other thing to note is that these graphs have symmetry, like we noticed before. So there's always a line of symmetry, and you could fold that graph in half and it would be equal on either side. So here, I'm going to highlight this in red. This is called the axis of symmetry, where you kind of fold it in half. So it's the line that is halfway through your parabola, axis of symmetry. So every parabola has an axis of symmetry. Some other things that we should know about parabolas are, we should know how to describe their domain and their range. Okay, so for the domain for every parabola is just all real numbers, because you can plug any x value into a parabolic function. So the domain is not restricted. We say x is in the set of all real numbers. And for the range, it is going to be restricted because you're always going to have y values being below a certain vertex or above a certain vertex. So we'll put always restricted by the vertex. Oops, I can't. Restricted. My pen's not working. Hold on. To above or below the vertex. Okay, and we'll practice writing the domain. Okay, so those are the keywords you need to know. You need to know the word parabola. You need to know the word vertex. You need to understand how to do the domain and range of a function and the axis of symmetry as well. So let's practice graphing a function from scratch by hand. So let's go to check your understanding number 1. And let's say we have to graph this quadratic function. We can see this is a quadratic function because it has an x squared term. So that's going to create that parabolic U-shaped function. So what we want to do straight away is just make a table of values. Oh, some parts of the screen are not working. I'm not sure why. table. I think it has to do with my cursor is in the way or not, or something like that. Okay. So we're going to have x, and then y equals, I'll rewrite the function here. It's 2x squared plus 4x minus 6. So for each x value, I'm going to be plugging it in. Now, I recommend using a calculator, and a lot of scientific calculators have arrow keys. And so once you plug in the function once, you can just go back and change the arrow keys to change the number. That's what I recommend doing, so you're not like putting in, retyping the whole equation every time. If you're not sure what I mean by that, just come and see me, and I will show you what I mean to save time. So what you're going to do, I'm just going to show you what to plug in once, and then I'm just going to write the rest of the numbers here. So you would put -4 into all the spots where there's an x in the equation, and just type that into your calculator. So type that in. You'll have 2 times -4 squared plus 4 times -4 minus 6, and you should get 10. You do that with -3, you'll get 0. With -2, you'll get -6. With -1, you'll get -8. With 0, you'll get -6. And you'll always see some symmetry coming out. Here, 1 will get 0, 2 you'll get 10, and 3 you'll get 24. So we can see here, this is the minimum point. This is going to be our vertex. You'll see on either side of that minimum point, you'll have the same values. So like -6, -6, 0, 0, 10, 10. And so there's that symmetry popping out. Okay, so let's actually graph that. They don't give you a set of an XY axis here, which I think is unfortunate, but we have to do our best to be nice and neat. So I'm going to usually just go by ones for the x values. I'll go 1, 2, 3, 4. 1, 2, 3, 4. And then for the y values, usually you want to go up by 2s or something bigger, because these curves can go up really high. So I'll go 2, 4, 6, 8, 10. -2, -4, -6, -8. Okay, so here's x, here's y. Okay, so let's put in our numbers. So the minimum point occurred at -1, and that was it. What is going on here? There we go. -1, -8. Something's happening with my pen today. It's really not agreeing with me. I'm going to just reset it. There we go. Okay. -2 was at -6. -3 was at 0. And -4 was at 10. And then I'll go on the other side. -6, 0, and then 10. So you should have complete symmetry there when you are graphing. And we're going to label a few things here as well. Okay, so let's label some key things. This point here right at the bottom, at -1, -8, this is the vertex. Okay, and the line of symmetry, the axis of symmetry would be right here. Axis of symmetry. It's right at x equals -1. On either side of x equals -1, the graph is identical. Some other things, we should write any intercepts that we see. So intercepts are where the graph hits the x and y axis. So these 2 points, I'll highlight them, are the x-intercepts, because it's where the graph hits the x-axis. I'll highlight those, x-intercepts, at x equals -3 and x equals 1. Not all parabolas have x-intercepts, because sometimes the graph, you'll see it's above the x-axis, but this particular graph, it does have 2 x-intercepts. And there is a y-intercept as well, right here. So lots to label. So that's where the graph hits the y-axis, and that happens at y equals -6. And then the last thing we can write down is the domain and range for this graph, which you should do as well. So the domain for any parabola, you don't even have to think about it, it's x's in R, meaning all real values of x. These arrows indicate that this graph is going to go on forever to positive and negative infinity for x. So the domain is not restricted. But for the range, we can see that the lowest point is at y equals -8. There are no y values that are a part of this graph that are below -8. So a way that we can say that is y is greater than or equal to -8. So that symbol there means greater than or equal to. Okay. Another way we can say it is y is in the set of values between -8 and infinity. We'll get to that later on as we go through the unit, how to use that type of notation if you didn't learn in grade 10. Okay, so that's kind of all the key words we want to use. The other thing I want to mention is that the x-intercepts also have another name. They are also known as, there's a couple of different names for them, also called the zeros of the function. The reason they're called the zeros is because that's where the graph equals 0. That's where the y value is 0. So if you set the equation to 0 and solve it, that's where that would happen. So they're also called zeros, and they're also called roots. We used that word a bit in the previous unit. So they could be called x-intercepts, they could be called zeros, they could be called roots. Those words are all interchangeable. Okay. One last thing I want to show you guys is just a little pattern that comes out when we look at the increases between values when you're looking at a parabola. So this is just on the next page. And we call it first differences. So let's look at this parabola here. And let's look at this table of values here. So here are some x values, they're just going up by 1. Here are the y values. Now on a linear graph, what you'll notice is the y values always increase by the same amount. But on a parabola graph, if you look at how the difference between the y values and how they're changing, it changes. So between the first y and the second y value, we can see it went down by 7. And then from -1 to -6, that's another decrease by 5. And then from -6 to -9, that's a decrease by -3. And then from -9 to -10, that's a decrease by 1. And then increase by 1, increase by 3, increase by 5, increase by 7. So like the points are getting kind of farther and farther apart. The jumps between them are farther and farther apart. And there's always going to be like a little pattern to it. And so you'll see that these differences always increase by 2. +2, +2, +2, +2, +2, +2. So you can actually look at a table of values and decide if that function is quadratic or not, just by looking at these first differences and seeing if there's like a similar pattern. Let me show you what I mean. Let's look here. I'm actually going to do the example this time and not the check your understanding. Let's look at these tables. Let's look at the one on the left first. And these are some x values here. And then these are the corresponding y values. And let's look at the differences between them. So from -4 to -2, that would be an increase by 2. And then from -2 to 0, that would also be an increase by 2. And this keeps increasing by the same amount every time. This would be a linear graph. This would be like a straight line on a graph because the y values are always increasing consistently. So let's look now at table B. Let's look at the y values and how much they're going up by. So from 1 to -4, that's a drop by 5. From -4 to -11, that's a drop by 7. And then from 11 to 20, that's a drop by 9. And then here's a drop by 11. See how the drops are different, but they're actually consistent, like they're going up by 2? That means this is quadratic. The first differences are decreasing by a consistent amount. Yeah. Okay. So you should be able to like look at a table and kind of decide if it looks like a quadratic pattern or a linear pattern. You can try these two over here. They're both linear. Okay. And lastly, we're going to just look at a way to use technology to solve some problems involving quadratic functions. A lot of real life sort of scenarios that involve quadratics are like projectiles, like when you're throwing something into the air. So let's say a projectile is launched upwards, so it could be like a rock or a ball or something like that, at a speed of 50 meters per second. So its height would be modeled by this equation here. So we're going to plug this into Desmos. Nice thing about Desmos is it's super quick and easy to use, plus 50t. So I don't need you to really write anything down for this one. We're just kind of looking at it. So I'm going to give you some Desmos tips here. Oftentimes, especially if it's a word problem, you'll see it kind of goes off the screen. You can easily sort of shrink your graph down. And if you just squish it in one direction, it just changes the y values. If you want to change the x values, you can do that. And if you want to choose both, you can do like more of a diagonal thing if you have a touch screen. Okay, so you can kind of zoom in and kind of see this here. There we go. Okay, perfect. And the other good thing about Desmos is it like gives you like the ability to kind of like click on important points here. So what the question asks is graph the quadratic function, identify and explain the significance of the intercepts and the coordinates of the vertex and the domain and the range. So we have to imagine this is an object. It goes up into the air and then it falls back down. So this highest point here would be like the highest height that this object reaches, and it reaches it after 5.102 seconds. And then this point here, after 10.4 seconds, we can see the object has hit the ground. The part that is below 0 would be irrelevant here because a negative height would not be like physically possible in this scenario. And same with like these negative x values, that would be negative time that doesn't exist. So really, this is the starting point. The object is starting 10 meters above the ground. It goes up, up, up. It reaches a height of 137.551, and then it goes down. And after 10.4 seconds, the object hits the ground again. So you should be sort of get comfortable with plugging in these types of equations into Desmos and then finding the vertex and the intercepts and interpreting what they mean. Okay, so that is the end of the lesson.